Hole cleaning in complex well bores such as extended reach wells, 3D designer wells, and wells with chronic well bore stability problems present unique challenges that require a complete systems approach to the overall drilling process. This presentation is a production of K&M Technology Group with assistance from BP and MI Swaco. The hole cleaning challenge begins at the planning stage of a well. Making sure that the well design focuses on the critical hole cleaning problems is a key element to the success of these wells. When these elements are overlooked, the inherent risk of these wells increases. The high-angle well drilling system can be viewed like this bicycle wheel, with hole cleaning at the center of the wheel and all of the other elements, such as the bit and BHA, the drilling fluid, the hole size and rig system, and any other elements in the drilling design or operations of a well tying into that system. Each element must then be considered in concert with the others while passing through hole cleaning prior to being utilized or changed. In this kind of system, no element can be considered in isolation. Once the plan is in place, the next step is to ensure that the entire rig team understands the downhole environment and the detailed response plan for tight hole. Understanding that tight hole in these wells is almost always cuttings related is the first step towards a successful well. The hole cleaning system can be divided into three distinct environments. The first is the near vertical hole section, which generally ranges from 0 to about 30 degrees. The next section ranges from 30 degrees up to about 65 degrees, and the final section is above 65 degrees of inclination. Each of these environments require a different set of rules for effective hole cleaning. Vertical hole certainly has its challenges. However, from a hole cleaning perspective, it is the easiest to clean. Normally, vertical hole cleaning is accomplished by plug flow of a drilling fluid that is designed to suspend the cuttings when the pumps are shut off. The cutting, in this case, has thousands of feet to fall before it reaches bottom. Fluid rheology is generally the key factor for effective hole cleaning in this section. A close-up of this zag tube clearly shows the slower hindered settling typical of vertical intervals. In this environment, as cuttings begin to move downward, they run into other cuttings. They also displace fluid as they move downward, which creates an upward flow that further slows the cuttings. In this clip, some cuttings are actually moving up the hole, others seem stationary, and still others are moving downward with the pull of gravity. As the angle increases over 30 degrees, new challenges begin to come into play. Watch how the settling environment changes as this zag tube is moved from vertical to about 45 degrees. Those cuttings that once had thousands of feet to fall now reach bottom in a matter of inches. Pipe that was once centered in the wellbore is now laying on the low side of the hole, and fluid that was flowing all around the pipe now primarily flows on the top of the hole. We'll get a better picture of the pipe and flow situations later on in this video. One phenomenon of cuttings behavior in angled well bores, called boycott settling, shown here at 45 degrees, shows the clarified layer along the upper side and the slump along the lower side of the tube. The boycott settling causes some particles to move upward with the flow stream. Others are momentarily suspended, while still others form a bed along the bottom of the hole and slump opposite to the direction of the flow. Here, a lightly dispersed mud is flowing at a 35-degree angle. Notice the rapid cuttings avalanching when the pumps are shut off. These cuttings will slide downhole until they pile up on top of the BHA or until they reach a high enough angle in the well and stop, creating a large cuttings bed. As the well inclination reaches about 65 degrees, the cuttings will stop sliding downhole. Now, instead of a large cuttings bed forming in the well, a long, more evenly distributed cuttings bed will develop. A very large volume of cuttings can exist in these hole sections. For example, A 2-inch cuttings bed in a 10,000-foot section of 12 1/4-inch hole is approximately 85 barrels of cuttings in the well. Here, dune transport, a form of saltation flow, is a typical transport mechanism. While this provides for a movement of a large volume of cuttings up the hole, it does not provide efficient hole cleaning. As we replay this clip again, notice how the movement of cuttings is very sudden, with almost no cuttings movement on either side of the dune. Movement of cuttings on a continuous basis only occurs on the top of these beds. Water in turbulent flow at 200 feet per minute in a horizontal well with drill pipe on the low side of the hole can efficiently clean the hole. The same water at 45 degrees, also with drill pipe in the hole, does not clean this interval at the same annular velocity. The net movement of the cuttings is downward, clearly showing that effective hole cleaning in one interval does not necessarily translate to effective hole cleaning in the next interval of the same well. An essential element of high-angle hole cleaning that needs to be understood is the fact that if cuttings are flowing over the shale shakers, the hole is being cleaned. The question now becomes, how fast are we cleaning the hole? Are we generating cuttings into this wellbore faster than we're getting them out? And is there a way that we can measure this? The first step towards answering these questions is to define the elements that affect efficient hole cleaning. There's no doubt that all of these elements play a role in how fast we're able to get cuttings out of the hole. Elements such as hole size, washouts, drill pipe size, and wellbore instability will affect my annular velocities, while flow rate, rotary speed, and mud rheology will play a role in how efficiently we're able to get cuttings out of the well. How the drilling fluid interacts with the rock that is being drilled is also an essential element of the hole cleaning system. If we are drilling with a dispersive system, where the drilling fluid can penetrate the cutting and dissolve it into solution, then most of the hole cleaning is accomplished through this mechanism. However, if the drilling fluid is fully inhibitive, such as this clear base oil, then the entire cutting must be removed from the hole mechanically. Each of these systems have their place in high-angle drilling. However, a very good rule of thumb is not to get caught in the middle between a highly dispersive and a highly inhibitive system. This clip represents a section through the high-angle portion of a wellbore. Here, the drill pipe lays on the low side of the hole, and the mud, following the path of least resistance, flows primarily on the top of the hole. In an inhibitive mud environment, the cuttings will lay on the low side of the hole, away from the fluid flow, thus preventing their efficient removal from the well. This computer simulation of fluid flow in a high-angle wellbore demonstrates the flow patterns as the centered pipe moves to the bottom of the hole. Very high flow rates are seen along the top of the hole, with little to no flow around the drill pipe at the bottom of the hole. Sweeps in high-angle holes have proven largely ineffective. This clip demonstrates how the sweep deforms and elongates along the top of the hole. If high-speed pipe rotation is introduced to stir the cuttings, the drilling fluid around the cuttings contaminates the sweep, destroying its original properties. This clip demonstrates how fluid flow in a concentric annulus on the left differs from that of an 80% eccentric annulus on the right. Note the flow filling the hole on the left and the flow primarily along the top of the hole on the right. In order to effectively remove the cuttings from the high-angle portion of the well, we must mechanically disturb the cuttings either with turbulent flow, which is impractical in hole sizes over 8.5 inches, or through pipe movement. Here, the addition of pipe rotation at 150 RPM effectively stirs the cuttings into the flow regime. Notice the hopping motion of the cuttings as gravity pulls them back out of the flow and the pipe movement pushes them back up. It's not just rotation that pushes the cuttings into the flow regime, but a combination of high rotary speed, pipe positioned on the low side of the hole, and mud rheology. Most of the hole cleaning takes place across the drill pipe tube. If the string isn't rotating, then the fluid travels along the top of the hole and the cuttings remain on the low side of the hole, resulting in no hole cleaning taking place. When slow rotary speeds are used, the energy that is transmitted to the cuttings through the viscous coupling between the pipe and the fluid isn't enough to move the cuttings into the flow on the top of the hole. The result is an inadequate hole cleaning system. As high-speed rotation is brought into play, cuttings are now transported effectively to the high side of the hole, thus allowing the fluid flow to move them out of the well. High-speed rotation must be maintained both while on bottom drilling and while off-bottom conditioning the hole in order to be effective. In order to maintain this viscous coupling between the fluid and the pipe, while still balancing the needs of the hole cleaning system with the annular pressure environment, we recommend a nominal 6 RPM reading of 1.0 to 1.2 times the hole size in inches. This ensures effective transfer of energy from the pipe to the fluid and then to the cuttings. The better the transfer of energy to the cuttings, the better the hole cleaning. Notice the poor transfer of energy to the cuttings on the left and the excellent energy transfer that is generating the helical flow pattern of the cuttings on the right. The importance of pipe rotary speed cannot be overlooked. The primary means of moving cuttings into the flow regime comes from pipe rotation. For hole sizes over 8.5 inches, rotary speed is the single most important hole cleaning factor in the system. Field experience has shown that cuttings flow over the shakers dramatically improves at high rotary speeds and that it dramatically drops off as the rotary is slowed. Hurdle speeds around 120 RPM and 180 RPM have been repeatable regardless of hole size, drill pipe size, or drilling fluid type. At these speeds, significant increases in cuttings flow over the shakers is generally observed. The hole cleaning environment in a high-angle well can be viewed like this conveyor belt. If the rotary speed and fluid rheology are not appropriate to get the cuttings onto the belt, then hole cleaning efficiency is going to suffer. Likewise, fluid flow rate represents the speed of the belt, and thus the rate at which cuttings are being removed from the hole. So, then is 120 RPM always required in the well? The answer depends on your hole size relative to the pipe that is in the well. The pipe hole area ratio, or FAR factor, is a measuring stick to help to determine which set of rules apply to a given hole section. If the FAR factor is greater than 3.25, then big hole rules apply. Alternatively, if the FAR factor is less than 3.25, then small hole rules will apply. This example of a 12¼ inch hole with 5½ inch drill pipe on the left has a FAR factor of 5.0, and the one on the right with 6 5/8 drill pipe has a FAR factor of 3.4. Big hole rules will apply in both of these situations, so a minimum of 120 RPM is required. In this 8½ inch hole example with 5½ inch drill pipe on the left and the 7 inch casing on the right, both FAR factors are less than 3.25, so the well can be drilled or cemented with something less than 120 RPM. If, however, 4 inch or 4½ inch drill pipe is used in 8½ inch hole, such as in these two examples, then the FAR factor exceeds 3.25 and big hole rules will apply. 120 RPM or higher must be used in these situations. In summary, hole cleaning efficiency is primarily affected by three things. Flow rate. Flow rate moves along the top side of the hole and acts as the conveyor belt moving cuttings out of the well bore. Rotary speed. Rotary speed acts to get the fluid moving around the body of the drill pipe, to throw the cuttings up into the flow regime. Rotary hurdle speeds must be met in order to maintain effective hole cleaning. And fluid rheology. Fluid rheology acts to create a viscous coupling with the drill pipe. It further acts to help suspend the cuttings momentarily in the flow regime. It also has to provide hole cleaning in the lower angle portions of the well bore. Getting the right combination of these critical parameters and then keeping them in the desired range throughout the drilling process requires full-time attention to detail. Good hole cleaning doesn't just happen. It requires a commitment from both the office and rig-based teams and a clear understanding of the downhole environment. Complex wells must be treated as an entire system with hole cleaning as the center of that system to achieve a successful well program.